we'll get started again. So I'm Brian Vanderwind. I'm, along with Megan, members of the HPC consulting team here at NCAR. We're going to go till noon, I believe, and then we'll have lunch. But Megan and I and others will be around in the afternoon. And obviously we have more tutorial sessions, at least one more, I think, in the afternoon. So this section is going to be a follow-on to what Megan presented. She went through a quick but I think pretty thorough overview of using X-ray. Now we're going to show how that can be coupled with Dask, which Megan talked a little bit about, to really scale up data analysis beyond a single core. So if you have a question in the room or you have a question online, feel free to post it. We'll monitor that. Generally looking for like clarification questions, things like that. And then if you have more, I guess, not unrelated isn't the right word, but you kind of know what I mean. If it's not directly related to the content, then we'll take those at the end of the session. All right, so in this tutorial, we'll start with the fundamentals and then we'll get more into the scaling and optimizing later on. So, brief overview of what Dask is. Dask is basically a Python package that enables task-based parallelism for Python data science. It's kind of a high-level elevator pitch, I suppose. So as a package, it's an open source Python library. So you can see and contribute and do all of that good stuff that we have with open source science. Basically, it allows us to scale the existing Python data science ecosystem. What does that mean? Things that you would commonly use in your notebooks like NumPy data structures and pandas data frames and X-ray, of course. Those can be extended to multi-core machines or in fact multiple machines, particularly when your data sets exceed the available memory that you might have on something like a laptop or a desktop. So this is a really powerful capability, and it's something that is already used extensively here at NCAR and I think in the university community as well. Broad question you might ask: why do we want to run our data analysis in parallel at all? Setting aside Dask for a second. So if you haven't done a lot of parallel coding, the nice thing there is as I said, it allows you to operate on data sets that are too large to fit into the memory of a single system. So a laptop like this, for example, it might have something like 16 gigabytes of memory. It's not too bad. But when you load data structures into Python, they tend to get bigger than they are on disk because there's a lot of metadata, and Python, frankly, isn't the most efficient all the time at using memory. So it can be helpful to extend past what we have, the limitations that we have on a single system. And that's true on like an HPC system like Casper or Derecho as well. You might have access to a single core in a session, maybe 10 gigabytes of memory, but we want to scale past that. And Dask allows us to do that in ways that are native to the system that you're running on, whether it's like an HPC system or the cloud or what have you. So another reason to run in parallel is that obviously task-based parallelism allows you to achieve speedups, potentially, depending on the nature of your problem and how you set up your code. So with task-based parallelism, what we're doing with Dask is we're splitting up our data into multiple, what we'll call chunks, and then we can operate on those in parallel, achieving those speedups. Now, there are other methods for parallelism in Python as well. You could conceive of writing some code with like MPI for pi, for example, or you can use multiprocessing. There's other libraries as well, there's quite a few. So why use Dask in particular? Well, as I sort of mentioned before, one nice thing about Dask is that it provides a familiar interface. So, if you're doing data science in Python, you're already using NumPy almost certainly. You're probably using X-ray in our community. You might be using pandas data frames. So when you use Dask, it basically allows you to extend your code that already runs in serial using those APIs with pretty minimal code rewriting. No massive code restructure typically is necessary. Certainly, you don't need to go in and write some C code and then bind your Python code to that C code. So there's it's it's pretty clean to make the migration to Dask. Now, if you get into optimizing your workflow and really trying to eke out every bit of performance, that can necessitate a bit more rewriting. But just getting up and running is usually pretty easy. Dask is obviously scalable. That's a big part of the reason why we want to use it. So the nice thing with Dask is with very similar code, you can still run on your single workstation, or you can scale up to something like an HPC cluster where maybe it's 100 or 1,000 times bigger than your laptop, or theoretically limitless if you run on the cloud. The only limit is your wallet. So that's really nice because we don't have to have separate code for the most part to run on these different systems. You can sort of migrate back and forth depending on the scale of your problem. And this also allows you to prototype your code on a resource that you have access to. So like I could write a notebook on my laptop here, a Jupyter notebook on my laptop, test it out at small scale, and then bring it to Casper and not have to do that prototyping, and use up my allocation on a system like Casper. Also provides flexibility. So Dask functionality, it's broken into a few different actually quite a few different component packages in the Python ecosystem. And some of those are interchangeable depending on the use case. So that's sort of what gives us that capability of switching between like a local setup and an HPC setup, is that we can switch between different Dask packages. And then finally, there are some pretty powerful built-in diagnostic tools. So Dask provides feedback via the client interface that you interact with your cluster, and we'll show that later. But there's also a bunch of really neat diagnostic dashboards. You can sort of see them not doing anything currently on the right side of my screen here. Try showing it this way. So like these will be populated with useful information once we actually set up a cluster and start doing computation. And that's really nice because like if you're using something like MPI to do parallelism, it can be really annoying, I would say, to do your profiling there because the tools, they're nice, but they're kind of user interaction intensive. Whereas Dask just gives you this information practically for free. And that can be really useful for identifying potential like performance bottlenecks and also debugging issues. Okay, so hopefully I've motivated why Dask is cool. But obviously we need to now kind of understand what Dask is. So teaching something like Dask is a bit challenging because all the concepts are extremely interrelated and you sort of need to understand like all of the components to actually use it, or at least a lot of the components. But I think maybe breaking down two fundamental concepts at the start makes sense. So what I want to talk about are Dask collections and Dask workers. Basically, a Dask collection is simply a data set that is using a chunked data structure under the hood. So, when you do a data science computation, you're performing some operation on a data set. If it's like a NumPy array, then you're operating on the entire array when you do computation. But an easy way to parallelize that is to split the data into multiple chunks. And Dask makes this pretty easy because it provides these pre-built data structures, these Dask collections, and there are high-level and low-level collections. The high-level collections are things like Dask arrays. There's also Dask data frames, which is a high-level version of a pandas data frame, and then even something like a Python list, if you have like unstructured data, it can support that as well. But certainly, typically, we're going to be looking at things like NumPy arrays and X-array structures. So this image, I think, kind of shows pretty nicely what's going on here. So you have this Dask array. This is a collection. And it's called a collection because really what it is it's a collection of chunks, and each chunk is essentially just a NumPy array. So if we focused in on like this single NumPy array or any one of these, really, these are all NumPy arrays, and you did an operation on that, that would be similar to doing to not using Dask at all. But what Dask is doing is it's taking all of these chunks and running your same command on all of them. Maybe not all of them at the same time, but a bunch of them at the same time. So it's a very convenient and easy way to achieve parallelism by just splitting up your data. And this is done via these collections. And as Megan mentioned before, since xArray can swap between NumPy arrays and Dask arrays as its core data structure, in essence, xArrays are a type of Dask collection too. There's a bit of a chicken and the egg thing here. But these can all be related. So if you have a Dask-enabled xArray, really what you're talking about is you have this Dask array instead of a single NumPy array, and then you have the metadata on top of it, which gives you your Dask data array. It's a lot of different array terms, but hopefully that made some sense. Okay, so let's think about this in an example, since we've kind of looked at this in a conceptual way. So as Megan showed before, at the end of the last session, we can load up a multi-file data set using this xArray method, openmf dataset. And I believe by default, it actually won't create a Dask array, but as soon as you give it this chunks parameter, that's going to, and you give it some value there, that's going to tell it, okay, chunk up this data that you're reading in from disk and use a Dask array instead of using a NumPy array. So what I'm going to do here is I'm going to use the same Lens2 data set that Megan used in the xArray tutorial. Here's just a bit of code. We're going to open up sort of the same variable, the reference height, temperature reference height. And then we're going to open up, I can scroll here. We're going to open up monthly data for a single ensemble. And what I'm going to do is I'm going to print the number of input files, and then I'm also going to print the size of the typical input file. So let's go ahead and run this. We see we have 9 files that we're looking at, and each one is about 14 megabytes on disk. So we would expect it to be a little bit bigger once it gets read in, and there's sort of all this metadata that Python tracks. So we're going to use that function, and again, the key parameter that I want to talk about here is just this chunks. So when you set chunks, then we should get our Dask-based xArray data array. So this is going to take hopefully just a moment here. It's done. Nothing exciting has happened because I haven't printed anything out, but this is now an object that's been created. And some of these other fields here are commented. Megan talked about a few of them, but you can certainly go into the xArray documentation and read more details about them if you're curious. So just as we did with the xArray earlier in the last session, we can look at the HTML representation in a notebook, at least. If you're running this in like a script, then obviously you're not going to be doing that. But there are ways to interrogate variables in a Python script as well. But in a notebook, we can get this HTML representation or repr of the data array. And we will do that here by just running this in Excel here. So now we're looking at the data array within the data set. And you'll notice here, this part looks a bit different than it would if it was a NumPy array. This is the representation or the repr of a Dask array. And this is sort of embedded within our representation of the data array from xArray. So we're getting all that information at once. And the really nice thing about this representation is it gives us information about the array itself and its memory footprint, but also the memory footprint of each chunk as it's been chunked by xArray and Dask. So you can see we have 9 chunks here. These are the sizes of the chunks in terms of the dimensions and the elements. And then there's the size in megabytes. There's compared to the size of the whole array. So this gives us a lot of nice information about the structure of what we've created here, along with the same usual like scientific metadata that we can get from xArray. Yes?
Is there an ideal chunk size?
Yeah, there's ideal chunk size is a challenge. There's typically an ideal range of chunk sizes for a problem, and I'll talk more about that later in the notebook. But yeah, that's a pretty complex topic. Yeah, so we've got a lot of information about our memory usage and also obviously about the data and the way it's laid out. You can also print out explicitly the the size of the chunks by referencing this chunks parameter. This actually gives you all of the chunks rather than the typical size. And one thing this can be helpful for is you can notice if, say, in one dimension, you actually have like a chunk of sort of leftover elements that's not quite the same size. That, depending on the number of chunks you have and the size of your problem, that typically doesn't impact performance as much as you might think, like not dividing perfectly evenly. There's typically other better reasons to define your chunk size, you know, to your point, Abby, and I think we'll show that a little bit more later. But as I mentioned before, you know, so we have 9 chunks in this Dask data, Dask data array, and then the size is given by these dimensions. If you were thinking back to the number of files that we have read in, you can see that we have the same number of chunks as we have files, and this is what OpenMF dataset will typically do. If in the absence of like any other specification that you gave it in terms of how to chunk, it will typically create a chunk for each file. That doesn't mean that you know, a chunk for each time. You'll notice that we have like 120 times in each of these chunks. But that's a general like expectation that you can get for the chunks when you do OpenMF dataset. Okay, so another thing, Megan alluded to this, but a core principle of these Dask collections is that it follows this concept of lazy evaluation, which sounds a little pejorative, but it's actually really helpful for us. So because parallel operations are often really, you know, they can be expensive in terms of CPU and memory requirements, we don't necessarily want to do those operations right away. We want to do them exactly when it's necessary to get our result. And at the other times, we don't necessarily want to keep that data in our memory, and we don't want to occupy CPU cores or use up allocation. So this allows us to basically define our workflow and define all of our computations, if we're careful, without actually triggering any computation until we manually ask it to do it. So when I created this structure up here, it didn't actually read very much of the data in. If you're familiar with the way data frames work in Pandas, it sort of does the same thing. It will read a tiny bit of the file information, just enough to give you useful information to decide what you want to do, but it's not reading in the entire data structure from disk. And that's pretty useful as well, because you might run out of memory if you're not careful. So just to prove this concept, I kind of want to show the memory footprint of the object, of the variable that we created, and then also show what it looks like if we do tell Dask to read that data into memory. So I've defined this little function here. It's nothing too mystical. It basically just prints the size in megabytes of our variable. So I will run this to define our function. Now, if I print the size of the collection variable before we do any sort of evaluation, you'll see that this responds very quickly because there's not really much data in it. And the size is essentially nil. If we printed this in bytes, there'd be a little bit of size just because we're storing that metadata, but it's basically empty. Now, if we actually want to get Dask to start using the data that's on disk, there's a number of ways that we can trigger that, but a typical manual way that you would do this is to use the compute method. If you run this on a Dask collection, that's going to tell Dask, okay, everything that you asked Dask to do with this collection, go ahead and do it. So you're creating an itinerary of tasks, and then when you run .compute, you're triggering the whole thing. So in this case, all I've done is I've created the collection. So that's sort of a load operation. When I run compute, what that's going to do is it's going to load the actual data in, and if I assign it to this variable here, then I should have essentially a NumPy array assigned to that variable, which I can then access using the .data field, just as I sort of accessed the data with the Dask array, but again, not really, because the data hasn't been read in yet. So I know Orhan and I were talking, or I guess Orhan and Megan were talking about this earlier, but this is something to be mindful of if you use the .data attribute. its behavior is different if you have a NumPy array, for example, or a NumPy-based X array, data array versus a Dask-based one. So if you run it on the Dask-based one, it's going to give you a representation of the data, whereas if you run it on a NumPy array, it's going to give you the data. So if I run this, we can see that now that I've asked it to compute, the size of the object has increased quite a bit. And it took longer because we're working with actual data now. Still not very long. But. So hopefully this gives you some concept that like you give instructions to Dask, but because it's doing lazy evaluation, that hasn't actually happened until you ask it to via a number of different ways, one of which is this dot compute. With Xarray in particular, you have these two different variants. So there's a compute method and then there's a load method. So above I showed dot compute, and what this does is it basically reads in the data and then is creating a new variable, essentially, new data structure. So you can assign that to a variable, as I've done. If instead you want to sort of modify your original variable and replace the Dask array with a NumPy array in place, you can do dot load. And you can see down here that that's basically the equivalent of doing like the data set equals dataset dot compute. So it's modifying the original thing, but in this case, it would be like ds dot load, and that would give you the same result. Okay, so that was a very brief introduction on collections, and we really only talked about like Xarray collections, a little bit about NumPy collections. As I mentioned, there's data frames as well. There's other forms of these collections, like you can have GPU-based collections that use CuPy. So there's a lot more to learn about collections, but only so much time. So we have like our data chunked up, but obviously that's not super useful until we can actually do computation and work on it. So this is where the concept of the Dask worker comes in. A worker is typically a Python process or another interpreter, and it's running either on the local host, like your laptop on a CPU core, or it's running on a CPU core on a remote machine. And when you trigger the computation, like we did before by running .compute, then you're assigning chunks of work to your pool of workers. So basically, the takeaway here with the workers is that the pace of the work done by Dask is most closely tied to the number of workers that are available. So obviously, if you have 4 times the workers, then ideally you could achieve 4 times the throughput because you're going to be able to work on 4 times the chunks simultaneously as if you had your original number of workers. And the number of workers is typically tied to the available resources. So again, on your laptop, your available resources is the number of CPU cores you have. That's sort of a hard limitation. A typical laptop would have anywhere from these days from like 2 to 16 CPU cores. So you could achieve that on a local machine. But again, on a system like Casper, you can scale up to thousands of workers. So that's where you really get large. You can do big data problems. There are other terms that I would say are not like maybe the 2 core concepts, but that we need to know them so we're speaking the same language as we go through future examples. So there's concepts of schedulers, clusters, and clients. And these are all components that we think about in Dask. So the scheduler, it's very similar to like a job scheduler in a sense, like a batch job scheduler in an HPC system or a scheduler on a cloud platform. Basically what it's doing is it's creating and managing task graphs or itineraries of work, and it distributes those tasks to the workers. So the scheduler is sort of coordinating what's going on in terms of moving chunks around. Now that plus the workers you can think of as a Dask cluster. And again, this is sort of an overloaded term because we might be thinking of like a physical cluster like Casper. But this is a software cluster. It basically consists of your Dask workers, and it consists of the scheduler that's orchestrating everything. And when you want to do anything on Dask, one of your first things to do is to define your cluster. So that's basically defining your pool of workers. But beyond that, you really don't interact with the cluster directly. Dask provides a high-level interface that you would use in your scripts or use in a notebook called the client. You instantiate a client, you attach it, you tie it to a cluster, and then you can use that to basically configure the cluster and sort of inspect the computation that's going on. And you might think, why are these separated? The big reason for that is the whole cluster part of it, the scheduler and the workers, those would typically all run on the same network. So whereas the client could run anywhere. So as long as you have access to that system. So in theory, I could run my client on my local machine and have that, if I had permissions to do so, have that talk to a scheduler that's running in a cluster that's running on a different system. And that's sort of the way the cloud model would work, right? Is you might have your cluster on a local machine, but then you might have your client on the local machine, but then the cluster is running in the cloud. Very briefly, just to tie this sort of into the packaging side of things, if you're like creating a Conda environment to use Dask, there's a bunch of different packages that can be relevant to the particular use case that we're talking about here, really the HPC use case. So you have your Dask package. This has sort of the core functionality. There's this distributed package, and that adds support for distributed clusters, which we haven't actually used yet, but we'll show soon. And distributed is also what brings in those cool dashboards that we'll show in a bit. There's this package Dask job queue, and that allows the distributed package to use HPC job schedulers as a cluster type. So pretty much you're almost always going to use that on a system like Casper. And then there's a Dask Lab extension, and this is what allows us to take those dashboard visualizations and show them directly in a Jupyter Lab interface. So that's like these little side panels that I have here. So that's a nice thing that you can use in like a typical Jupyter Lab. There's other Dask components in the Dask ecosystem that I won't really go into today, like Dask Cloud Provider for working in the cloud. If you click on this link in the notebook, you can see this whole ecosystem and all that there is out there. Finally, when you're working with Dask, since we actually ran compute, and remember we loaded in data, it's a good idea to kind of clean up after yourself. This frees memory and also can sort of terminate this very simple cluster. So I'm going to just go ahead and do that. And that way, I won't end up in a scenario where I have like multiple clusters running at the same time and I end up getting confused. Okay, so that's the first part. That's really just the Dask fundamentals. But now we can talk about scaling up using distributed. So we technically did create a cluster above. It was a very simple non-distributed cluster as sort of the base case that you wouldn't typically really use when you're doing more complicated computation. But once we bring in the concept of the distributed cluster, that's when we really can scale things up. So there are many different types of distributed clusters that are provided in this Dask ecosystem, but I'll briefly talk about two of them. So there's sort of the most simple one is called a local cluster. If you start up a local cluster, it's basically going to size itself to the number of CPU cores that it can see on a local machine. Like if I was running it on this laptop, it would see all the CPU cores that I have there and try to use them. This is, again, pretty nice for prototyping, but obviously you can't scale past the physical constraints of the computer that you're on. If you were to start one of these up, it's very simple. You would just do from Dask distributed, you would import a local cluster object, and then you would instantiate it here and assign it to a variable. And at that point, I basically have a local cluster that has n workers, which is the number of cores that it can see. We're not going to use this in this tutorial. We're going to focus on the PBS cluster, but just keep in mind that basically using a local cluster for a lot of these examples would just be like a simpler case of what we're already doing. On the other hand, what we're going to use is a PBS cluster. This is a type of HPC cluster provided by that Dask job queue package. And this allows us to create Dask workers within scheduled PBS jobs on the HPC system. There's also obviously like a Slurm cluster. There's LSF, SG cluster. There's different ones for different types of HPC job schedulers. There's a Kubernetes cluster if you're using Kubernetes. But they all sort of work fundamentally pretty similarly. Okay, so let's get into it. The reason that we're using this is using a job scheduler is really a defining part of using an HPC system, as I'm sure you're all familiar with. So when you go on a system like Derecho, for example, you end up on a login node. You have access to a limited amount of resources. If you use too much of those resources, somebody like me will probably email you, be grumpy. Really what you want to do is you want to get access to those compute nodes, and you have to do that via the job scheduler. So when we use Dask, it's really no different, and that's what this PBS cluster allows us to do. So if we're using a PBS cluster, the first thing that we're going to do, similarly with the local cluster, is we're going to import it. So from this, we're going to import it from the Dask job queue package. So I will go ahead and run this. And notice that we're also importing the base Dask package as well, because that provides the core functionality of Dask. Now, this is I guess the biggest area where the complexity is a bit higher than the local cluster. So we need to define how we're going to interact with the HPC job scheduler. And really all that we're doing when we define the cluster here is we're sort of giving a template to spawn batch jobs. And this is very similar to like the directives that you would give at the top of a batch script. And they'll be specific, some of these settings will be specific to which job scheduler you're using, like PBS or Slurm or what have you. So in our case here, I've sort of organized these fields into different categories. So there are some here that are just basic job directives. You can give like a job name. You should give the queue. In this case, we're going to use Casper. Give a wall time. Typically, your workers would run much less than an hour for various reasons. I give it an hour here just because I want to sort of have the same workers for demonstration purposes here and hopefully not fight too many people in the queue. You need to give a project code to charge against. Side note, if you run this notebook yourself, change the project code because this one is one I use and it won't work for you. Give a log directory. This helps us sort of put the logs all in one place, the job logs, and these will also have logging information from our workers. And this, by giving a directory, it basically allows us to not sort of pollute the same directory that we have our notebooks in and make things hard to find. Now in this next section, these settings impact the resources that get assigned to each job that gets created when you scale up your cluster. So in this case, I want each job to have one core, one CPU core, 4 gigabytes of memory. And then since PBS sort of has a complicated resource assignment structure, they just have this resource spec field. And this is sort of where you define your select statement as you would if you were submitting a job in PBS for HPC work. So this we want to basically match here. So 1 core, 1 NCPU, and 4 gigabytes memory, 4 gigabytes memory. Now there's this processes field. This is different from cores. This defines the resources that get assigned to a worker within the job. In this case, they're equal, but they don't have to be. I'll talk a little bit about that in a second. There's also, you can provide a directory where Dask will spill data. So if you're not familiar with the concept of spill, basically if you run out of memory, an application can then spill data. It can write data to disk temporarily so that your program doesn't crash. This is nice, but data that's been spilled to disk causes your execution to slow down a lot. So you generally want to avoid that if you can. But this tells it where to write that spilled data. And then finally, you want to give a network interface on a networked cluster. In this case, on Casper, just take my word that you'll use EXT. One thing to note, you used to use IP0, which would be InfiniBand, but in some recent changes on Casper, we've moved from exposing InfiniBand for this purpose to exposing a high-speed Ethernet network. It should give you very similar performance, but if you do IP0, like in an old notebook, you'll get an error on Casper. One thing, so I'll run this, and we'll see if I get this. I guess I'm on a node that's not very occupied. If you are on a shared system and somebody else is running a Dask cluster on the same node, then you may get a port in use warning. This isn't something to be concerned about, but it's helpful if you accidentally start 2 clusters yourself. It'll sort of give you a bit of a clue to that. It didn't pop up here, so I guess we don't get to see that. One other thing to note here, PBS, the job scheduler, uses GB to mean 1024 based, like 1024 megabytes per gigabyte, for example. But if you were to use GB as your units in Dask for the worker, that would actually give you 1000 megabytes per gigabyte. So this GIB and this GB here are actually the same. That's a little bit of a nuance that you kind of just have to remember for this use case. Okay, so the other thing I talked about is how to choose the number of workers per job. This is something that is it's case dependent, basically. I would say typically using one worker per job is a nice default. Using less workers, or in fact one per job, that's generally going to increase your job throughput in most batch schedulers because it's a system like Casper is tuned to schedule small jobs before big jobs. But it's also easier to backfill small jobs. So if there's like a tiny gap in the job scheduler, in the calendar where it can fit that small job, it's going to do that. But if your job is too big, it can't fit it. So it can't execute backfill. You'll always avoid interpreter lock issues, and interpreter lock is a whole, we don't have time for that. But look up the GIL, the GIL in Python online if you want to read some fierce debate. But you can avoid sort of your code deadlocking in certain situations if you always have sort of one process per job. It's conceptually easy to understand. I think that's the biggest benefit really to using one worker per job. Because each HPC job you can easily correlate to a running worker. It might be more robust if the system is for some reason unstable. Like if a job fails, you lose one worker instead of losing like 10 workers or something like that. And sometimes you can speed up file reads in certain situations because if you have different workers running on different nodes, they each sort of have their own bit of bandwidth to the parallel file system. So that can be a small optimization. There are certain circumstances where using more workers per job will be beneficial. If you have very thread-friendly workflows, like NumPy can use like threaded math routines behind the scenes. Those can actually sometimes run faster if you have multiple threads running your work on the same host. And then it might allow for a slightly higher memory threshold because the workers are all going to share a memory pool versus having their own distinct memory. It's like just a bit of flexibility, but generally that's almost noise. So again, I would say tend towards using one per job unless you have strong reasons to do otherwise. Okay, so I talked a lot about defining the cluster. A big tip, I would say always check your sort of template JavaScript that the cluster will try to submit before you actually create any workers. This is a nice check to make sure what you're doing makes sense. So if you run this JavaScript method on the cluster, it's going to print out what looks like a PBS JavaScript because it is. And this, every job that gets submitted by Dask is going to look like this. So here I can check that my account is defined properly. And I can also check that this stuff down here, the command that to start the worker actually makes sense as well. So, I have one thread per worker, that's good. I have 4 gigabytes memory per worker, that's good. Okay, so let's actually spin this up. Again, our portal to working with the cluster is this client object. So I'm going to go ahead here and create it, which I've now done. And in a notebook that's in a properly set up environment, this is going to give me access to this HTML representation of the client is going to give me access to my dashboard and also the dashboard sort of visualizations in the Jupyter interface, Jupyter Lab interface. So if I click on this, now we're in the dashboard. I realize I should probably get out of full screen so I can switch between tabs. But so this provides us a ton of information about what the cluster and what the workers are doing. And we'll talk more about this when it's actually doing something, because then it'll be more interesting. But that's going to be very powerful. And then if I click this, now our tabs here in the Jupyter Lab are giving us information as well, or they will be once we do something. You can also drill down with this wrapper on like details about the cluster. So I can see the total number of threads, the total amount of memory across the cluster, the number of workers. This is all 0 right now because we haven't actually started any. But if you were to display the client again later, it would provide some of that information. Okay, so just briefly, the dashboard, it provides us a lot of nice visualizations. In particular, some that I want to highlight are like worker memory usage. So you can get the memory that's being occupied by data on every worker. This is obviously pretty nice to make sure that you're not running up against the memory limitation. You can track your task progress, so you can see how far along you are in the task graph that you create. So again, a task graph, like step 1 might be like load the data, step 2 might be some addition, step 3 might be a reduction. And as you go through that task graph, you can see that happen sort of in this task stream visualization here. You can see CPU utilization. I don't have that up here right now, but you know, that sort of tells you if your CPU cores are busy. Oops. And then you can also, not so much in in these panels, but in the actual dashboard, there's this info tab as well. And from there, you can see a bunch of log information. So like if I wanted to see the scheduler log, I could click this, and this will give me, you know, alerts basically from the scheduler. And if I had workers started up, I could see their logs from this interface as well. We'll go back to the main one here. Oops. Okay. Also, like this tabbed interface, you can save your window layout here as a workspace and load it in the future. That's sort of a Jupyter Lab feature that can be pretty nice if you use this a lot. Okay, so let's go ahead and scale to make these visualizations more interesting. So remember, we need some workers to actually do any work. So it's very simple to do this. Basically, all I need to do is take my cluster object and scale it. There's a bunch of different ways to scale it. You can scale it by resources. You can scale it by, you know, what have you. But here, we're just going to scale it by number of workers. Since we have 1 worker per job, we're also going to create 2 jobs. Now, one thing I'm doing here that you might not typically do is I'm going to run this wait for workers function. So this is going to wait for 2 to have started up. Typically, like you would just let the workers start doing work as soon as they exist. But here I want to wait just because I'm sort of demoing everything. It could also be useful if you're benchmarking your code, because if you have all the workers started up, it's going to run faster than if only some of them started up. So now that I've run this, you can see it's sort of blocking progress until all of our workers exist. And in this worker memory one, I can sort of tell that I have 2 workers going on here because I have these 2 bars. This gives their memory usage relative to what I've allocated to them, which remember is 4 gigabytes per worker. You can also print out worker information from the cluster object. So like here, if I just printed the .workers attribute, I can see this dictionary of workers, the 2 workers. And then I can also get this from the job scheduler, since these are PBS jobs. So the bang symbol here, that basically says run a shell command, if you're not familiar. So here I'm running the qstat, which is giving me information about the jobs I have running. So here I have my main job, which is running my notebook. And then I have my 2 workers. And this is where, like, if you give your workers interesting job names, you can search for them in like your job scheduler. That can be useful. Keep in mind that since these are HPC jobs, as soon as we scale the cluster up, the clock is ticking on them, like the wall clock that you've allocated. So you don't just want to like scale your cluster up until you're ready to do work. Here, you know, they're going to sit idle for a little bit because I'm talking, but in actual work, you'd want to time that appropriately. Okay, let's do some computation. So as we did before, I'm going to use the same Lens2 data, but now instead of doing the monthly data, I'm going to use daily data with basically the same ensemble and the same variables. So here it's again going to be 9 files, but now the files are 438 megabytes instead of, was it like 14. But we're going to read things in the same way. So you notice that this OpenMF dataset call doesn't really look any different than it did before when we were using a very tiny Dask cluster. Again, I have the chunks equals auto. The one difference I'm doing this time is I'm specifying this parallel equals true. as Megan mentioned, I think in the first session, what this does is this causes the data loading to also be parallelized. So both of my workers are going to work on loading data into this variable at the same time, once we actually ask it to load data, which we haven't done yet. This is a nice optimization on an HPC cluster, for example, because you typically have access to a parallel file system. If I use that on my notebook does not have a parallel file system. So it wouldn't be beneficial there. We can inspect the data just as we did before by looking at the repr. So here now you can see the chunks are quite a bit bigger. We have 60 chunks now, so I guess they're actually 60 files. And the total data set that we've read in is 6.47 gigabytes. So now we're getting into the size where like doing computation on this could actually become a challenge on the laptop. We could read the data in, but if we create any sort of other variables as a result, we might start to exhaust our available memory. This is where Dask becomes useful. Yeah, so we loaded 90 files in. We now have 90 chunks. And the thing is, the variable is larger. Again, not actually read in yet, but it will be once we start reading in data to the workers. So as an example here, let's just do some basic X-ray operations. I'm not going to really go into what these are because hopefully you got that out of Megan's session. But again, the key is that we're using Dask under the hood now instead of so let's get the reference temperature at Boulder. Again, we can do our lat lon selection and use the nearest. Again, so I've run this, it returned very quickly. It did not give me any answer. And if you'll notice in these dashboard visualizations, nothing has really happened. We can look at the task stream. I guess we do have this here. This just opened the data set to query some metadata. It didn't actually read anything yet. And then in the progress, nothing is happening except it's refreshing. And then we haven't really changed anything in terms of the amount of data read into the workers. That's all thanks to that lazy evaluation. And we can get some information about what will happen. There's a couple of ways to do this. Sure, more than these two, but the two that we typically talk about, if you run this .dask, if you get this .dask attribute, this will give you sort of a high-level graph of or high-level view of what the task graph looks like, or again, the itinerary of things that Dask is going to do. So again, like it's going to open the data set, it's going to concatenate the data set into a single chunked object, and then it's actually going to get the data. So that's what we've asked it to do at this point, along with doing this selection. If we want to visualize this, we can use this visualize method. This is, it's very parallelized, so it can be hard to see. If you double click on this, you can actually see it in full size, but this can be helpful, I think, for very deep task graphs where you have a lot of different operations happening and you kind of want to see the flow of where your chunks of data are going to go. In this case, we're not doing a very deep task graph. We just have a lot of different chunks that we're operating on. So we get something that's very wide, but not very deep. But you can sort of see like the different indices in terms of like the chunk that it's going to operate on. Going into the power of that is a whole other talk as well. This also gets saved as a file in your like local directory, so you don't have to necessarily look at it in the notebook. However, we aren't finished constructing our task graph, so I also want to do a resampling and take the mean. This is going to, give us, our nice graph here eventually. So you notice still nothing has happened. We're still sort of being lazy here in terms of what we're doing with that. We've assigned our result to this variable TB mean. However, that variable doesn't have any result in it yet. We could run .compute to get that result, but there's other ways that you can trigger a computation in Dask, and you have to kind of be mindful of when these might happen. So a plot operation, for example, actually triggers a computation. And that's because if we want to create the plot, we obviously need a result. So Dask is aware that, okay, I need to actually do some computation now. So if I were to run this, now in this progress screen, we can see a whole lot of stuff going on. And these are sort of the different elements of that task graph. I like looking at the progress screen because it gives me some idea of like, how far along we are for each of the, various components of the computation. And then, the bytes stored per worker, now that we've read in data, actually hasn't changed all that much. This is probably overkill in terms of what I've allocated to these workers. So that's something really nice about these visualizations is you can get an idea of like, okay, well, am I actually asking for a reasonable amount of resources for my cluster? Maybe I'm asking for too much, maybe I'm asking for not enough. But you can see I've got my result here, so that's nice. And since I ran the time magic on this cell, I can see that the wall time taken for this operation was about 16 seconds. Not terrible, maybe, who knows, without context. But to get some context, we can do some scaling. So what I'm going to do here now, and this is where Dask is really nice, is I can sort of just immediately scale up my cluster, as long as the job scheduler has available resources to give me. So here I'm going to scale to 4 workers. And again, I'm going to wait for them all to start up before doing anything else. You might note, if you're looking at this carefully here, that so now we have 4. That was fast. Thank you, PPS. That the original 2 weren't recreated or they weren't restarted. Those original 2 workers I had are still just sitting there. They're waiting, to do computation, but they are the original workers that we had. And these 2 new ones now are sort of evident by the fact that they haven't had anything written to their memory. Let's rerun that same computation. So here I'm just going to do a compute. I don't want to look at the plot again and fill up my notebook, but it's doing the same exact thing, except now with double the number of workers. And we should see a reduction in the compute time, hopefully. Yeah, about 50% reduction. So that's good scaling. Very happy with that. You won't always see perfect scaling like that, depending on the nature of your problem. But in an ideal world, that's the kind of thing you want to see. It's actually a little bit better than 50%. So great. That's sort of exactly what we'd expect to see in this case with doubling the workers. So that's your first order optimization, I suppose, is like think about the number of workers that you need for doing your computation in the amount of time that you want to spend. Like any other sort of parallel computing, it's a trade-off, right? It's more expensive to use more workers, but generally you're going to have a faster time to solution. Now, since those 2 workers were existing before, one thing to be mindful of is if I look at the job scheduler output from QStat, this is a bit wrapped. Let me see if I can unwrap it. In this last elapsed time field, you'll notice that the old workers have used 9 minutes of their wall time and the new workers have used 1 minute. So if you're running a notebook that lives for a long time and you do this sort of scaling up from a small cluster to a large cluster, just be aware that you're going to have a mishmash of like different amounts of time remaining on those workers, on the jobs that are running those workers. So in some circumstances, it can actually make sense to like scale your cluster back down to 0 and like totally refresh to have new workers to make sure that they all have the same amount of time to run the computations. That's a particularity, I guess, of using the job scheduler approach here. Okay, so that's really the fundamentals of scaling up in an HPC context. So now I just want to talk a little bit about particular optimizations you might do, as well as debugging. A very simple debugging example. Debugging Dask is quite complicated. We spend a decent amount of time in consulting on this, and I know the ESDS folks spend time consulting people as well on Dask failures. So this is barely scratching the surface, but I just want to give some basics. So in terms of optimization, there's a couple different things we can think. There's a lot of different things we can think about, but a couple that I want to point out. One is this idea of persisting data. So when you run .compute, what you're doing is you're asking Dask to run those operations and return data to the whatever system is running your notebook. So you can think of it as sort of like local memory versus worker memory. If instead I wanted to keep data in my worker memory past when the computation will be done, I can tell Dask to persist that data. And that can be useful if like you have a bunch of different computations that all have the same like first 3 steps, but then maybe have a different final step or something like that. because you don't want to have to redo those first 3 steps over and over again. If you were doing serial computing, this would be the same idea as having like a temp variable that's holding, an intermediate result, and then you do your final step multiple times on that temp variable. Here we're doing the same exact thing, except our temporary variable is actually data that's kept on the workers instead of kept locally. So an example that sort of demonstrates the power of this persisting is, let's say we wanted to calculate 2 different time means in the same like lat-long box. So if we were to naively do this and get the summer average and the winter average, so like if I look through this command, basically I'm selecting across a lat-long box, just a random one. And then I am filtering by season, June, July, August, and December, January, February. And then I'm taking the mean, and then I'm computing to get the result. Here in this sort of naive approach, I'm actually repeating this lat-long subselection twice. And if I run this, we'll see this is going to compute now. I guess while this is running, I'll show what the task stream output looks like as well, when it's not refreshing. So we can see that, I guess it's zoomed out a little bit as well. But you can see what's sort of the different operations are being done by the workers. And I like the progress screen a little bit more personally. Okay, so now it's done. We have these 2 averages for the summer and the winter. And this took 14 seconds, not bad, I guess. But if we were to persist, what we want to persist in this case is our lat-long box. So we're going to subselect that and then keep the subset in worker memory. And then all I'm going to do is do my seasonal subselection and computing of the mean instead of doing the whole shebang both times. And I time this, we should see a noticeable difference. So again, we have to do the box selection, which is really what takes the majority of the time. But then these other 2 happen very quickly, and we get an end result that takes about 7 seconds instead. And you can imagine that if we were doing a very complicated example with like a very big data set, this is a huge optimization. The problem with persist, though, is obviously it's keeping data beyond when it's necessarily needed, at least according to Dask, in worker memory. So if you're not careful with persisting data, you can exhaust your worker memory and cause the workers to get killed. This is why you wouldn't just persist your entire data set in worker memory generally, because a lot of data sets are too big to do that. That would really only make sense, by the way, if you had like 1 chunk per worker, which is typically not the case. You're going to typically have more chunks than you have workers available. It's also extremely important to clean up when you're done using persistent data, because otherwise it's going to stay in worker memory. So you can do that by just running a delete on sort of your intermediate variable. So in this case, if I run delete on subset, it will free up the worker memory for you. And one tell on whether something is persisting in memory that I think is really handy, this progress screen sort of actually gets locked to the operation that created the persistent memory. So you see these aren't going away. And that's sort of an indication to you that, oh, okay, I've got some data that's being persisted in the workers. And if I run delete on this temporary variable, it should clear out our progress screen. So yeah, there we go. So that, I think that's a handy, quick thing, and a bit of information you can get from the dashboard here. Which, speaking of, let's kind of just look at the full visualizations here. So if I go into the full dashboard, again, I can sort of see the total memory of the cluster, the bytes stored per worker, the task stream. I can get more information specifically in this worker screen. This, oops, I clicked on it. This sort of gives us like the address of the workers. It gives us information about like what it's doing in terms of disk IO. So you can get a lot of metrics out of this. A lot more than you might get from the visualizations that you can fit in your Jupyter Lab interface. It's going to get pretty messy if you try to look at all of this at once. But I like to have ones that I find particularly useful in this screen. Yeah.
How did you get from this screen to the full dashboard?
Oh, yeah. So I just have them as separate tabs up here, but yeah, when I started it up, that was from that cluster object, or sorry, client object. So if I go back up to here, where I printed the HTML representation of the client, it gives you this HTML, this
Okay. Thank you.
HTTPS link to the dashboard. Okay. So another optimization that we can think about, and this gets back to Abby's question about chunks. So choosing chunk sizes is certainly an important thing to think about when you're using Dask. Thus far, we've let Xarray sort of decide our chunk sizes by giving it the auto option. But you can specify them manually, and in fact, if you're using something like NumPy or Pandas, it might be more typical to do so. The chunk size that gets chosen can be quite impactful on your performance. So in general, regardless of the type of collection you're using, you can think about, there's sort of a trade-off between like load balancing your problem and the overhead that you get. So if your chunks are too small, you're going to end up spending a significant, probably wasteful amount of time waiting for Dask to do overhead. So things like scheduling tasks, data communication, sort of assigning chunks to different workers, all that stuff, it doesn't take a lot of time, but if you have a ton of chunks, that overhead can start to add up relative to the time that you're spending computing. On the other hand, if your chunks are too large, you run the risk of spilling memory to disk, which will slow everything down, or in fact running out of memory and running into failures. And the scheduler can also have a more difficult time load balancing. So the extreme example of that would be, let's say you had 4 workers and you had 3 chunks. Then I'm going to have one worker that's constantly idle, and that's not efficiently using my cluster. So having a too small collection of too large, in terms of memory, chunks is not great. That said, it can be tricky to figure this out. So we do have some general rules of thumb. In general, like a chunk that's say 100 to 500 megabytes, or maybe greater than or equal to 1 million elements in size, that tends to work pretty well in modern systems. Not universal, but if you're somewhere in that range, that it's going to feel like a good place to be. And remember that the HTML representation that Dask gives provides the chunk memory footprint. So that information is super easy to get. It always makes sense to check that before you start kicking off your computation. One other consideration with chunking, particular to using certain types of data, is matching the file chunking. So again, we have an overloaded term here, but data formats like HDF5 and NetCDF4, since it uses HDF5, those files are themselves chunked. And some, it's just like a chunk size that's the entire data. But if you look at some NetCDF files, it's actually broken down into different chunks, like chunks of data, and you have a total number of chunks in that single file for each variable. If you don't adhere to that chunk layout that the file has when you create your chunk layout in your Dask collection, that mismatch can cause inefficiencies in the way Dask is going to do the computation. So it's best to specify Dask chunks, like chunks in your collection, which are either equal to, or better yet, multiples of the chunk size that's given by the file. So let's demonstrate this, and hopefully that'll make sense. So I'm going to look at a different data file here. This is from a model forecast over the Arctic. It's stored in NetCDF4 format. This is again on Blade. So if you're running on our systems, you would have access to this file. We'll open this just using Open Dataset. It's not a multi-file, so we're just going to do Open Dataset. But we are going to let it chunk. So we're still going to get a Dask Dask-based data array back. And we're going to let it auto chunk, as we've done before. So the nice thing in Xarray is it actually gives you an interface to query both the chunking of the Dask object and the chunking that it sees in the NetCDF file, and we can see how those line up. So if we print our repr of the data array, we can see that the chunks here, the shape of the chunks is 2 by 32 by 710 by 710 in terms of elements. We can see that the size is within the range that we consider good. It's within 100, between 100 and 200, or sorry, 100 and 500. And then in terms of matching the file chunking, is there a question?
There is a clarification question online from Mari, which is asking, are the chunks based on the size of the file you're reading in? So with respect to the whole CSM2 member file that was read in, for instance.
So in terms of the Dask collection chunks, those chunks, again, were automatically chosen by Dask. In this case, the chunk size is going to generally, it's going to span the entire array dimensions, but the chunks will generally be split across the time dimension, because that's generally the moving dimension in an etcdf file. And it's going to split those chunks based on the number of files that are part of your data set that you're reading with the multi-file read. So it's not necessarily based on, it's sort of based on the size of the file, in that all the elements in a single file are going to comprise a chunk in terms of the collection. Hopefully that clarifies. If not, let us know. Thanks for the question. Okay, so if I look at there's this encoding attribute of a xarray data array. And if I print that, I'll get a lot of information, but there's a particular item in the dictionary called chunk sizes. And this actually gives us the chunk sizes of the data when it's in the netcdf file on disk. And if we look at what xarray has chosen, we can see that the Dask chunks are in fact a multiple of the file chunks. So this is good. This is kind of what we want to see. And I'll show why we want to see that with some performance, hopefully. But you can see basically it's double the size of the file chunks. So it is a multiple. So let's do a little bit of performance benchmarking to show the impact of this. So here I'm just going to, I'm going to take the max across the num net grid levels dimension, and then I'm going to compute. And we'll time this, shouldn't take very long. And I like to run this a couple of times just to avoid any sort of like data caching optimizations that the file system might do. So we can see that the wall time, when I let it just auto chunk, and again, I'm telling you, just take my word for it, that the auto chunking did a good job. So we have a wall time of 1.48 seconds. But we can actually manually specify chunk sizes. And that's what I'm going to do in this example down here. Now, one thing that might make sense in other contexts would be to look at the size of our data structure and say, okay, well, let's choose a chunk size that evenly divides into this data structure so that we get like nice uniform chunks. And since if I look up here, you know, let's say I just used all of the times, but then I used, you know, half of each spatial dimension, you know, then I'm going to get like sort of a nice grid of 4 chunks, and it's going to evenly divide. That seems very, very nice. I'm already getting a warning from xarray, which is great. So xarray is telling me that the specified chunks, they separate the stored chunks, or the chunks in the file, along 2 dimensions, and that could degrade performance. So I think this is a really great thing that xarray has added to sort of give you information as the user in terms of maybe you're doing something that's not ideal. But we're going to do it anyway. You'll see how it looks. So if I now print the representation here, again, this looks really nice. I've split my array up beautifully into this cube of 4 cubes, or I guess 8 cubes. So yeah, that seems like it would be good. But if I run compute on this now, because the chunk size in Dask doesn't match the chunk size in the file, it's leading to data movement between the workers, because different workers are having to do IO operations on multiple of the file chunks. So it's basically leading to an inefficiency in the IO portion of the operation. And we can see that, and to be fair, run this multiple times as well. We can see that now the wall time is 2.4 seconds, whereas with the optimal configuration, it was 1.5 seconds. So that's a pretty significant degradation. And again, if you had a big operation going on, that could really add up. So fortunately, X-ray has gotten a lot better with this in terms of its auto chunking. This was kind of a more interesting example the last time I did this tutorial a year ago, because the auto chunking would kind of give you bad chunks, and manually specifying it was often a good idea. But this has been improved a lot. And now I would say the auto chunking is giving me a really nice result. It's going to be hard to beat, to be honest. So this leads to sort of a general Python tip. Keep your packages up to date. If you're using a version of X-Array that's like 2 years old, you might get that bad auto chunking. And I would say don't use it in that case. But really what I would say is update your version of X-Array and your versions of Dask and all that. That's typically going to lead to less bugs and better performance. Also, just some good practices when you're using Dask and X-Array. So similar to the Dask data frames, like Pandas data frames in Dask, it's more efficient to first do your spatial and temporal indexing and filter the data set early in the pipeline before you do like a resample or a group by, because those operations are more expensive. So you want to reduce the amount of data that you're actually running those operations on. So think about the order of your task graph as the takeaway there. We talked about chunk sizes. It's pretty much always better to chunk along the time dimension, and that's why OpenMF dataset does that. When it's creating your chunks, it's really doing it along the time dimension. That's helped along by the fact that model outputs and things like that are typically written. The files are split based on time. And Megan talked about apply ufunc. So when possible, apply an unvectorized function to the X-ray object. And I think Megan has offered to talk more about that in the afternoon session if you want more details on apply ufunc. Okay, so real quick, let's just talk through a quick debugging case study. This is pretty synthetic, so it's my one synthetic example, I suppose, but hopefully it will show the impact of memory usage on workers and also where we can get a little bit of information about that. So in this section, I'm going to synthetically create NumPy arrays of increasing size to the point where first I'm spilling to disk, and then I'm causing the workers to be killed, essentially, because they've used too much memory. And these thresholds can be set in Dask. These suggested thresholds, I believe, are the defaults. So if you use 60% of the available memory on a worker, it will start to spill to disk, 60 to 70%, depending on different memory types. We'll get into that. New data allocation is paused if you hit 80%. It's going to try to finish the allocation that's already going, but it's not going to start a new data allocation. And then if you hit 95% of the memory used, it's going to kill the worker and then basically restart the worker. And the point of that is it's a safety measure to prevent your job from dying in addition to your worker dying. But it also, like if you keep encountering that condition, eventually the worker will give up and your entire computation will fail, as we'll see. You can change these. So depending on the configuration of your system, you may set different thresholds, but these are the suggested ones. So let's import a Dask array. And this is like the Dask version of a NumPy array instead of an X array object. And then I'm going to import this logger function from distributed. What this allows us to do is actually write log messages to our worker logs. This is probably not something you're going to do very often, but I want to sort of insert some information into our worker logs that we'll then inspect. I'm going to define this function. It's just going to note in the worker logs what the current chunk size is in megabytes that the worker is handling. And then I have this loop here that's basically going to, again, allocate bigger and bigger random NumPy arrays until we get to about 4 gigabytes here, this 3900. And what I'm going to try to do is trigger those different thresholds that I talked about. So if I go ahead and run this, what I want you to do is pay attention, especially to this worker memory dashboard. And what you'll see, and I'll just go ahead and run this so see it. And the first time, everything is great. It's all good. The second time, we start to get these yellow bars, and the yellow bars indicate spilling to disk. So that's something to look for in this visualization. Then I start to get red bars, and that means that we're in that allocation is paused regime. Now, in this last attempt, you'll notice that these bars are actually disappearing, and that's a sign that your workers are getting killed. Now, Dask will then recreate your workers, so you'll notice they get killed and then they reappear, and then they get killed and then they reappear. That'll happen a few times until Dask eventually says, okay, I don't think there's any way I can do this. I'm gonna give up and give you an error message. And if we scroll down in this error message, this already gives us some good suggestions, I would say. So it says it attempted to run the task, and it gives you sort of the long ID for the task. On 4 different workers, all the workers died in trying to run it. Inspecting the worker logs is often a good next step to diagnose what went wrong. So, and obviously you can visit this website to get information as well. But let's look at these worker logs. So if I run this shell command here, I'm basically just sorting the files in my worker log directory by modification time. So if I look at the last 4, these should be files that we care about for the workers that just got killed. So if I go into, not in my directory, get there, so. Notebooks, and then task logs. I can also look at this based on modification time. So if I look at, I'm gonna guess it's this one because it's newer. Nope, that's the wrong one. It's creating an output and an error log, as schedulers often do. You could join these if you give special settings to your JavaScript, but I did not do that for this case. So now we can look at our worker logs. This is sort of looking at it in a text editor. Let me close this so it doesn't word wrap as much. But now we can see the messages that we wrote, like current chunk size and the size of them. And then we can start to see some of the messages that Dask is putting in these logs. Like, hey, the unmanaged memory use is high. This may indicate a memory leak or memory not being released to the operating system. And then it's telling you, okay, well, the memory is getting really high. And then it says, okay, we're pausing the worker. And then we say, oh, well, the worker has exceeded 95% of the memory budget, so I'm gonna kill it and restart it. There's this process called a nanny process, which sort of manages the workers. Cheapy name, but it's what restarts this worker a bunch of times until it eventually kills. Now, again, this is a synthetic example, so I know, obviously, that we're exceeding memory. But the take home here is that maybe you're running your notebook and you're not paying attention to it. It's running in the background when you're doing other things. If you go back and look at your worker logs, the job logs in this case, you can look for things like, hey, unmanaged memory use is high. And that might give you an indication that you had some spill to disk while you were running your workflow, even though it didn't fail. So looking at those logs can be. And also, as I mentioned, you should be able to get these logs from the dashboard as well. So like if I click logs here, well, I guess it refreshes it, so it doesn't show you the previous workers that were killed and restarted by the nanny. So I guess it's better to look at the JavaScript. But if it wasn't killed, then you would see a summary of what happened to the worker in this output. Okay, so just to wrap up, because I know we're getting close to lunch. Just some resources here in terms of more information. There's so much more about Dask that I don't have time to talk about in an hour and a half. But some of these links should be good places to start. And these links will give you some locations to ask if you have questions. Hopping on the ESDS Zulip is a great place to ask questions about, Earth science, particular Dask questions. So I would highly recommend using that as a resource. I do want to pause if there are any questions, but I do have a couple of supplemental things I could talk about as well. Yeah, go ahead.
I have a question on that last example for the So in my experience, I've gotten that before and it's still kind of vague. Like, what are the first things you would look at to fix it? Like do you increase the amount of workers? Do you check your chunk size, like all of that?
If you were running out of memory or spilling the
Yes.
disk? Yeah, so I think, if it's easy to look through the order of your computation, I would say that would be a good place to start in terms of fixing the problem, because that's really, I think that's often better than like just throwing more resources at the problem. That said, generally you're pretty, you're gonna be pretty satisfied with the way you've set up your computation, or it's just gonna be like too time intensive to really do a deep dive on optimizing the order of operations and things like that. So yeah, you can, like on an HPC system, you could just ask for more workers and more jobs. That'll give you more, more access to resources, and then you could have more chunks, right? So that's the key, right? Like if you just give more workers, but the chunks are still just as large, it's gonna fail in the same way. It's just gonna happen on more workers. So you can make the chunks smaller, and then you would typically compensate there by maybe adding a few more workers. Or you would just say, okay, it's gonna take a little bit longer because I have more chunks, but it still fits now.
What about like the size of your workers, what you allocated to them?
Yeah, so that's another knob, of course. You could increase the memory of each worker.
Is there a benefit to more workers or memory per worker?
That's a job scheduling question. So I think if you have a quiet system, and it really depends on what your system is constrained by. So I can tell you, because we look at Casper a lot, memory is often the resource on Casper that's harder to get than CPU cores. So I would say on Casper, you're probably better off asking for more workers and smaller chunks than asking for workers that have more memory, because it's going to be harder for those to schedule. But if you were on a system where like memory was super easy to get, then sure, add more memory to the workers. There's performance considerations potentially in Dask, but I think your bigger impact's probably going to be on the throughput of starting up the workers. As long as your chunk size still fits within sort of the recommended guidelines, because that is going to be a bigger performance impact.
When Dask starts spilling to disk, is it good about cleaning up after itself? Or, I mean, if it's spilling to your local directory on Scratch or something, do you have to go in and, I notice I have to delete a lot of log files and whatnot, but I never seem to have to delete any data that gets spilled.
Yeah, I believe it should clean up once that data is done being used. So like a case where it would not clean up what we do is if you were persisting memory, right? Because then not only would it be persisting what it can fit in memory, but it'd be persisting the leftover spilled stuff onto disk. I guess we could take a quick look just to see, since we've done all these. So if we go to local, well, I guess that's going to happen on different hosts. So that's not a super quick thing to demonstrate, but yeah, I would expect that it would do some cleanup as long as it's not actively needing the data. And I guess spill is a bit complicated on a system like Casper because we also have a spill space for the job itself. So it's a bit confusing in terms of which spill you're using.
If you configure it the way Brian showed, where you're spilling to local Scratch PBS job ID, that directory only exists for the duration of your job ID. It's created empty. And even if your job aborts abruptly, it will get cleaned up by the scheduler.
Oh, wow.
So, but if you run it elsewhere, your mileage may vary.
Yeah, that's true. You don't have to worry about like kind of polluting the system after your workflow is done. The only thing I would say you'd have to maybe worry about is like running out of spill space, but at that point, your problem is just probably too big for any replicable system. Because we have two terabyte NVMe storage on each of these nodes that sort of backs up, and some portion of that is used for spill. Right, you had another question?
I do. So I've noticed using Dask on Casper, sometimes when it's building the Dask graph, I'll be watching the dashboard and I could wait an hour for it to build the Dask graph. It seems like it's doing that in serial. And then once that's done, it'll actually start doing the job. So yeah, I don't know if that indicates a problem with my process or something. And sometimes I get a notification or a warning that my Dask graph is unnecessarily large or something. And so I don't know if does that tell you something about what I'm doing, or is that normal for that Dask graph to be processed in serial?
I would say that that's normal. I think you can do a threaded scheduler. Yeah, Megan says yes. So that, then you would be able to give more CPU cores on the local, like where the scheduler is running. I guess not necessarily local. But you can assign some CPU cores to act as threads for the scheduler, and that might help. I haven't run into that scenario too much because, I'm doing more instructive examples than like super big data analyses. But yeah, I think in general that will be sort of a sticking point with Dask because that part by default is not going to be super parallelized.
Yeah, so your cluster sits there idle while you're,
Yeah.
waiting for your Dask graph to compute. That seems like a bottleneck.
So what I suggest is not, you're using Dask distributed, I think. So what I would suggest to do is either is going like on a batch node with like more memory, like for example, a little bit more memory, and then not use Dask distributed and see if that will parallelize it. Because not using Dask distributed still uses the threads. For example, like if you choose a PBS, for example, batch job from when you're like creating your from Jupyter Hub, when you're creating your session, if you, for example, select your selection, for example, if you increase the number of threads, and then if you land on there and not use Dask distributed, automatically what Dask does is that it will use the single machine scheduler. And the single machine scheduler basically detects what are the resources available locally. It's very similar to the local cluster, but it's all behind the scene. And it automatically detects the threads and the memory and everything. And sometimes that's beneficial. So if you do that, then you'll understand if like that happens like serially or that happen like serially on that local node, for example, if you're using login and then your cluster stays all idle, or if it's if it's like communication issue between your cluster and your like head node, or if it's like another issue with overall like the task graph generation. Does that make sense?
Somehow different than local cluster.
So the thread of the scheduler, single machine scheduler and local cluster, they are very similar. They automatically, the single machine scheduler, it either uses the threads or the processes that are available on your machine. So you can use local cluster instead. That's totally fine. It translates very well there, but just removes the complexity of the Dask distributed from the user. So still uses all, like if I don't use Dask distributed altogether, for example, on my laptop, it still use all the resources that's available on my machine in parallel, but it doesn't show like a client, it doesn't show all that. So yeah.
Yeah, thank you for that tip.
Yeah, I'd say we could talk more about that in the afternoon session if you'll be there,
Yeah.
but we are up against lunch, so I'm gonna call it here. I do want to point out that there are a couple of supplemental topics in here that you can check out at your leisure about adaptive cluster scaling, we can talk about, and also using configuration files. So it's a bit more information if you want to check it out on your own.